Myself, Dr. N.C.H. Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's session on Laurent series Part 1. In the last session, I have introduced the Taylor series expansion of the given function of complex variables f of z, and the Maclaurin series expansion. So the Taylor series expansion is about a point z equal to a or in powers of z minus a, whereas this Maclaurin series expansion is a subcase of Taylor series expansion, and we expand the given function in powers of z. That means about a point z equal to 0. So if we expand the given function about z equal to 0, that expansion is called Maclaurin series expansion. So these two were discussed in the last session, and today I am going to introduce the next expansion, which is called the Laurent series expansion. So first I will introduce the Laurent's theorem, then the Laurent using which we can find the Laurent series expansion of the given functions. So finding the Laurent series expansion, and we solve some problems on Laurent series also. Now, the Laurent's theorem. Here, let C1 and C2 be two circles given by mod z minus a equal to R1 and mod z minus a equal to R2. So that means there are two circles, we can say concentric circles with different radii. For example, so this is the one circle and this is the second circle. So this is C1, C2, and this region is called annulus region, the region between the two circles. Let f of z be analytic function on C1 and C2 and throughout the region between the two circles. So in this annulus region, and z be any point in the ring shaped region. So I can consider some z here between the two circles. Then according to this Laurent's theorem, the expansion of f of z can be in two different terms, the sum of two different terms. In the first term, we have the powers of z minus a as positive, and whereas in the second term, the power of z minus a is negative. Here we have z minus a power n. If you write this in the numerator, that becomes z minus a power minus n. So sigma n equal to 0 to infinity a n z minus a power n, and sigma n equal to 0 to infinity b n by z minus a power n, or b n into z minus a power minus n, where a n and b n are given by these two formulae. By integrating along the two circles, we can find a n and b n. While finding the Laurent series expansion, no need to evaluate this directly depending on the given region of validity. We can express the function as a Laurent series. So the integrals here taken are in anti-clockwise sense, and the series, this series is called the Laurent series expansion about z equal to z naught. Now here points to be noted. If z equal to a is a point of analyticity for f of z, the Taylor series expansion is unique and at its region of validity, whereas there can be different Laurent series expansions according to the regions of validity. So if there are different regions of validity, then we can find out different Laurent series expansions, but for Taylor series it is unique. Now, coming to the problems, here the first one, f of z is 1 by 1 minus z into z minus 2. Find the first one is Maclaurin series expansion, second Laurent series in the annulus region 1 less than mod z less than 2, that means the region in between the two circles, and the third one is for mod z greater than 2. So let us start the solution part. Now given f of z is 1 by 1 minus z into z minus 2. So let us simplify this first. So here by multiplying with minus sign, minus 1 by, here if we multiply with the minus sign, this becomes z minus 1, z minus 2. Now both are in the same format. And actually we need to find the partial fractions for this. So you know the procedure of finding the partial fractions, or else sometimes by direct simplification also we can split this product into sum of two functions. So by direct simplification, for example here this minus 1 can be written as z minus 2 minus z minus 1. I am trying to get the same terms in the numerator. So in the denominator I have z minus 1 and z minus 2. Now I am using those two terms to express this minus 1, so that it can be simplified in a simple manner. Now you can cross check this, z minus 2 minus z plus 1. So z minus 2 plus 1 is minus 1. So minus 1 can be written in this form. Now which is in the form of a minus b by c, which is a by c minus b by c. So split this into two parts, z minus 2 by z minus 1 into z minus 2 minus z minus 1 by z minus 1 into z minus 2. So these two gets cancelled. That's why I simplified the numerator using the same terms which are present in the denominator, so that this expression becomes 1 by z minus 1 minus 1 by z minus 2. So this is the given f of z. Now we need to find the series expansions one by one. So we have, what is f of z? 1 by z minus 1 minus 1 by z minus 2. Now the first problem, the Maclaurin series expansion. Maclaurin's series expansion. So this is about z equal to 0, and here it is very clear that here the singular points are z equal to 1 and z equal to 2, and z equal to 0 is a point of analyticity. A point of analyticity. That means this z equal to 0 is not a singular point. So therefore the Maclaurin series expansion is possible. We can find out the Maclaurin series expansion of the given. What is the given function? 1 by z minus 1 minus 1 by z minus 2. So we know how to find the Taylor's or Maclaurin series expansions. We use the standard known expansions. So let us take minus common here. This becomes 1 minus z minus, here also minus common, so plus 1 by, I am taking 2 common, then 1 minus z by 2. So this can be written as minus 1 minus z power minus 1 plus 1 by 2 into 1 minus z by 2 whole power minus 1. Now use the standard expansions like 1 minus x power minus 1. If both are negative signs, we will get all positive terms. So 1 plus x square plus x cube plus so on. So using that, f of z equal to minus of 1 plus z square plus z cube plus so on plus 1 by 2 into 1, both are negative, so 1 plus z by 2 plus z by 2 whole square plus z by 2 whole cube plus so on. Hence f of z is minus of 1 plus z square plus so on plus 1 by 2 into 1 plus z by 2 plus z square by 4 plus z cube by 8 plus so on. So this is the this is the Maclaurin series expansion of the given function. Here the first expansion is valid for mod z less than 1 and the second is valid for mod z by 2 less than 1. That means mod z less than 2. So hence both the expressions are valid for mod common region mod z equal to mod z less than 1. So, like this we can find the Maclaurin series expansion. Now, coming to the second B bit, Laurent series expansion in 1 less than mod z less than 2. Laurent series in 1 less than mod z less than 2. So, the region, given region is 1 less than mod z less than 2. So, that means this is the region between the two circles mod z equal to 1 and mod z equal to 2. So, here we can consider two circles, one with radius 1 and the other with radius 2. So, this C1, C2, and here some point in the annulus region. Now, here mod z equal to 1, and here we need to find the Laurent series expansion. Here the first one is 1 less than mod z less than 2. So, 1 less than mod z, that means mod z is greater than 1. So, if you consider this reciprocal of this must be less than 1. So, this series expansion must be valid for mod of some z less than 1, and that's because of that reason we try to get these terms 1 by z in the expansion. Similarly, mod z less than 2. So, this is, if you divide it by 2, mod z by 2 less than 1. So, in one expansion we must have 1 by z, and in the other expansion we must have z by 2. Now, let us consider the given f of z, 1 by z minus 1 minus 1 by z minus 2. Just now I told one expansion must contain 1 by z and the other z by 2. So, here I will take this z common so that I can get that 1 by z here, 1 minus 1 by z, minus in the second expansion we must have z by 2. So, here I will take this minus 2 common, then 1 minus z by 2. So, this becomes 1 by z into 1 minus 1 by z power minus 1 minus minus plus 1 by 2 into 1 minus z by 2 power minus 1. Now, we can expand these two using the standard expansions. So, 1 plus 1 by z plus 1 by z square plus 1 by z cube plus and 1 by 2 into the same thing. Here now we have z by 2. So, 1 plus z by 2 plus z square by 4 plus z cube by 8 and so on. So, this is the required Laurent series expansion in the given annulus region. And here it is very clear that the first expansion is valid for 1 by z less than 1 and the second is valid for z by 2 less than 1, which is mod z less than 1, which is mod z greater than 1. So, the expansion is valid for both 1 less than mod z less than 2. And coming to the third one, we need to find the Laurent series expansion in the region mod z greater than 2. Mod z greater than 2. So, that implies mod z by 2 greater than 1. So, mod 2 by z is less than 1, and try to get those 2 by z terms in the expansion. So, what is the given f of z? 1 by z minus 1 minus 1 by z minus 2. So, here the first one, as usual, we take z common, 1 minus 1 by z, because here the region is only this mod z greater than 2, and now I need 2 by z. So, z, that means z should be taken common, 1 minus 2 by z. So, this is 1 by z into 1 minus 1 by z, which is the same, and minus 1 by z into 1 minus 2 by z or minus 1. Now, we can expand this using the standard expansions. Plus 1 by z square plus 1 by z cube plus so on, minus 1 by z into 1 plus 2 by z plus 4 by z square plus 8 by z cube plus so on. So, which is valid for the given region. So, like this we find the Laurent series expansion of the given function. Coming to the second problem, we need to find the Maclaurin series expansion as well as the Laurent series in the given region. Let us consider the function f of z, z plus 1 by z minus 1. First we will simplify this, then we find the expansion. Now, once again, similar to the previous problem, here we try to get the same term which is present in the denominator in the numerator. So, in numerator try to get the same term. So, let us write z minus 1 first, but it must be z plus 1. So, add 2 so that this becomes z plus 1. Now, f of z is z minus 1 by z minus 1 plus 2 by z minus 1, a plus b by c. So, which is 1 plus 2 by z minus 1. Now, the first one, Maclaurin series, is the series expansion about z equal to 0. So, f of z is 1 plus 2 by z minus 1, can be written as 2 by minus 1 common, then 1 minus z, 1 minus z. So, 1 minus 2 into 1 minus z power minus 1. Simply expand this using the standard expansions. 1 plus z square plus so on, which is the Maclaurin series expansion. And now, the second one is Laurent series expansion in mod z greater than 1. So, second one, mod z greater than 1, Laurent series expansion. So, mod z greater than 1 means mod 1 by z is less than 1. So, try to get these 1 by z terms in the given f of z. What is given f of z? 1 plus 2 by z minus 1, 2 by z minus 1, and we need to get this 1 by z terms. So, I will take z common, 1 minus 1 by z, which is 2 by z into 1 minus 1 by z power minus 1. So, 1 plus 2 by z, 1 plus 1 by z plus 1 by z square plus 1 by z cube and so on, which is 1 plus 2 by z plus 2 by z square plus 2 by z cube plus so on, which is the Laurent series expansion in the given region. Let us solve one more problem. Given f of z is 1 by z square into 1 minus z, and give two Laurent series expansions in powers of z and specify the region in which they are valid. Here, first series, there exist two different Laurent series. As we discussed in the introductory part, the Taylor series expansion is unique for the given region, but here if there are different regions of validity, then we will get different Laurent series expansions. So, the first Laurent series expansion, f of z is 1 by z square into 1 minus z. Simply expand this using the known expansions, standard expansions, 1 plus z square plus z cube plus so on. So, by multiplying with this 1 by z square plus 1 by z plus 1 plus z square and so on. And here this is valid for mod z less than 1. This is valid for, since it is having powers of z 0 less than mod z less than 1. Similarly, the second Laurent series expansion, the second expansion, what is giving f of z? 1 by z square into 1 minus z. z square into 1 minus z. So this is 1 by z square. Now I'll take z common here, minus z common, then 1 minus 1 by z. So this becomes minus 1 by z cube, 1 minus 1 by z whole power minus 1. Now let us expand this 1 minus 1 by z power minus 1 as 1 plus 1 by z plus 1 by z square plus 1 by z cube and so on. Using 1 plus x whole power minus 1 is 1 minus x whole power minus 1 is 1 plus x square plus x cube and so on. All the terms will be positive. So by multiplying with this minus of 1 by z cube plus 1 by z power 4, z power 5 and so on. And here this is valid for mod 1 by z. So valid for mod 1 by z less than 1. That implies mod z greater than 1. So this is the reason of validity. Like this, we can find the Laurent series expansion of the given function with respect to the given region. Today, we have discussed about the Laurent series expansion. So how it will be and the problems on Laurent series expansion. So for the given function f of z in the given region, we can expand this as a power series expansion using the Laurent's theorem. In the next session, we will continue the same. We will solve some more problems on Laurent series expansion. This is for today's session. Thank you very much.